Hello dear students, I hope you and your family are well and safe. So as you know, I was supposed to see you more often in the second part of the module. I can't see you, but I will be publishing some material a bit more often now. So you can expect each week to have a short video, especially with some applications in R and maybe some maybe an extra PDF with some additional solved exercises. So in particular with the video today, we will see how to evaluate PDFs, CDFs, quantize and to sample from distributions, plus a very short simulation to showcase the central limit theorems. Please let me know if anything is unclear, get in touch as I'm super happy to help. Enjoy! So, in the lectures with Marina, you have seen some discrete random variables, such as the binomial, the Bernoulli, the Poisson distributions, and some continuous random variables, such the exponential, the normal distribution, and so on. So, with this video, I'll show you how you can use R to deal with these distributions, and in particular, we will learn how to evaluate PDFs, evaluate CDFs, evaluate quantiles, and very important, how to sample from these distributions. So you will have this script along with the video. While I'm explaining these things to you, I'll be coding, so sorry for the waiting times every now and then. Okay, first thing we look at is how to evaluate a density. So the functions in R are very easy to remember. To evaluate a density, you have to combine the D for density plus the distribution token. Okay, this will be very clear in a second. So, for example, if we have x, which is distributed according to a Poisson with parameter 5, so lambda equal to 5. And I want to evaluate the density, so the probability mass function of this random variable. So that would be the probability, for example, for x to be equal to 3. Okay, so without the R functions, we'd have to use the formula. So this will be the exponential of minus lambda, that is 5 in this case, times lambda, that is 5, to the power of k, okay, k is 3 in this case, divided by k factorial, so factorial 3. So the result, and let me remind you that to run a line from the script, you have to press Ctrl Enter or Command Enter if you're using a Mac. So this the PMF of a Poisson with rate 5 evaluated at 3 is 0.1403. Right. There's a much faster way to do this. And it's to use the inbuilt R function, which is D for density, and distribution token for the Poisson is Poise. Okay, so this function evaluates the probability mass function of a Poisson distribution. I want to evaluate the PMF at 3, and okay, look here, we have some suggestions. So if you want to use this function dpoise, we have to specify x, which is the point at which the PMF will be evaluated, and the lambda, right? So this is done in this way: poise 3, lambda equal 5. Command Enter, the result is the same, all right? So with these functions, you can easily evaluate the PDFs and PMFs of the most common random variables. So, for example, if I want to evaluate the density function of the Poisson at 5, then this is how it's written like. This function, dpoise, works in a vectorial way. It's vectorized. What does this mean? So if I define a vector, so let's say that I define the vector s equal 0 to 15, okay? So with this command, let's see what s is like. So we have defined a vector s You can see it here in the environment. S is 0, 1, 2, 3, 4. So 0. So with this command, you just like define a vector with all the numbers, all the integers from 0 to 15. And if you write S and you press Command Enter, then this is what the vector is like. So if I write d poise, right, and I evaluate the density instead of just for a point, but for a vector, and we'll stick to lambda equal 5, right? The result will be a vector with the same length as S, so 16 entries, and each entry will have the density of the Poisson evaluated at 0, 1, 2, 3, and so on. So this is very useful if, for example, we want to plot this probability mass function. Okay, so to plot this function, S will be all the numbers, all the integers from 0 to 15. D is the Poisson probability mass function evaluated at these points, right? And to plot these two together, okay, the command, very straightforward, is plot, and I specify S, okay, which is what goes in the x-axis, and y, so the density. Let's see what we get, okay? So these points represent the probability mass function of a Poisson, okay? So maybe we'd like it to be a line, so this is easy to do. So if you change the type of the plot and you set it to L, okay, this will become a line. Other things that you can easily do with a plot is to change the label. So the X label will be, well, instead of S, usually we use X. Okay, this is changed. And the label for Y will be PMF of Poisson with lambda equal 5. Okay, and so we have also this label is changed. Great, so another simple example is to, we can plot the PDF of a normal this time, a normal distribution. So if X is distributed according to a normal distribution, let's say with mean 2 and variance 4. We want to plot the whole PDF, so we need again to set a sequence of numbers where the PDF will be evaluated. So this time we're dealing with a continuous distribution, so it's not enough to specify S as a set of integers. We will define S as a sequence that goes between, let's say, -10 to 20, with increments of, let's say, 0.1. Okay, so now S has become this vector, you see? So there are all the numbers from 10 to 20 with increments of 0.1. The function to evaluate the density will be D for density plus distribution token. The distribution token for the normal is just norm, so very easy as you can see. D norm, so evaluated at these points with mean. We have to specify the mean, and be very careful here. So in the function D norm, we don't have to specify the variance but the standard deviation. So because the variance of our normal distribution was 4, we want to specify the standard deviation is 2, okay? And again, we can copy and paste this command, plot. It will plot points with x coordinates S and d coordinates D, okay? Type is fine, xlab is fine, and this will be the PDF of a normal 2, 4, okay? Let's see what we get. So don't forget to compile these lines, and this is the PDF of a normal distribution. Okay, so for plotting curves, points, and whatever. There are very powerful graphical packages in R. This is not the most powerful package, it's the most basic one, but you can do basically everything with it. Maybe you won't get like very fancy graphs. If you want to get fancy graphs, get in touch and I'll give you more details. But the key package is ggplot2. So this package will allow you to create some very, very fancy graphic. Great, so this is done. The next thing we look at is how to evaluate a CDF, okay? Great. So we start straight away. So the command to do this is very similar to the PDF. So P for probability. The probability distribution is a synonym for CDF at times, plus the distribution token. Great. So we start straight away with an example. So the example is if x is distributed according to an exponential with parameter 1. All right. So, and we want to calculate the CDF at 2. So that will be the probability for x to be lower or equal than 2. Okay. So usually we'd have to calculate the integral. So recall that the PDF of an exponential with the rate 1 is just e to the power of minus x. So if you integrate the exponential of minus x, you get minus the exponential of minus x. And you'd have to calculate it from 0 to 2. That will lead to exponential of 0 minus the exponential of minus 2. So this is the CDF of the exponential evaluated at 2. 0.864667. Great. Faster and general way to do it is P for probability and distribution token. The distribution token for the exponential is exp. Great. So I want to evaluate the CDF of the exponential at 2. Okay. And here I have to specify the rate. That will be the lambda of the exponential distribution. So the rate is 1. The result, of course, is the same. So, okay, let's have a look at the graphical interpretations of this, even though it's very easy, but it's good to learn how to use certain commands. So, for example, if I define S as the sequence from 0 to 8 with the increment 0.1. If you use this, I don't remember how to call this, like semicolon, and then you rewrite the name of this vector. On top of defining the vector, you will have it displayed in the console. So let's check this. Great. So I've defined the vector S, and S is 0, 0.1, 0.2, up to 8. Great. So now we look at the density. I define D as the density of an exponential evaluated at these points, and we've said that the rate is 1. Great. So as before, I'll just like copy and paste what we've done before, right? The PDF, okay, so we're not talking about CDF, but PDF, because like I've used the D here, right? Of the exponential, I'll just change this PDF of exponential with parameter 1, and we should have the plot. Okay, it looks very plausible. So we have plotted the PDF of the exponential just to recall that the CDF of the exponential evaluated at 2 is just like this area below the curve before 2. There's a way to visualize this area, but this is optional. So you can skip this if you are in a hurry or whatever. It can be useful at times if you want to highlight an area. So the command to highlight the area is polygon. Okay, the command polygon connects so you have to specify a set of points by specifying the x coordinate and the y coordinate. So, for example, if I want to plot a polygon with vertices 0, 0, 2, 0, and let's say 1, 1, okay, I will have to specify the x and the y's as two vectors. So the first point is 0, 0. The second point is 2, 0. And the third point is 1, 1. X, y. Now, if I use the function polygon x, y, I will have the triangle I'm searching for. So, this is not what we're interested in, though, in this case. We want to plot a polygon that goes all around this curve, then down here, then to 0, and then up again. Okay? So, our polygon, our axis will be defined in a different way. So first I have to define the axis of all these points here, okay? But these are just like these points. We've defined them already. These are S. However, I don't want all S, because S, recall, is a sequence from 0 to 8, okay? I want all the S's, all the entries in S, such that S is lower or equal than 2. The Y's of all these points are the values of the density, but only when S is lower than 2. Okay. However, so with these two commands I've specified all these points. Okay, I'm missing 2 points. I still want to connect 2, 0 and 0, 0. So I concatenate these vectors with the points 2, 0 and 0, 0. I define my x, my y, and this is the polygon I get. So this is the area. Okay, we're not doing fancy graphics. However, let me just do a couple of things. So I want this area to be red, and I specify density of 10. This area becomes filled with red lines. Okay, it's nicer. Okay, so this is to say that the red area is 0.864667. That is the CDF evaluated at 2. Okay, so end of optional. I will use the polygon again later on, but just to showcase some things. Don't worry about it. So of course, we have displayed the PDF here. We can easily display the CDF. Copy and paste these two commands. Now we don't want to evaluate the density, but the CDF. Okay, so okay, we can call it P. Why not? P will be the CDF of the exponential evaluated S, and then I'll plot S against P, and this will be the CDF of an exponential. Great, and this is what it looks like. Last thing I'll show you is, okay, sometimes we might be interested in computing the probability for x to be greater than 2. Well, this is easy, right? So this will be 1 minus the CDF of the exponential evaluated at 2. So in particular, this will be the exponential of minus 2, okay? And indeed, you can do it like this. So 1 minus px of 2 with rate 1, so px, sorry. So of course, you get the same result. However, sometimes it's easier, it's tidier to do it this way. So p, the exponential of 2 rate 1, and we don't want the lower tail. We don't want the lower tail of this CDF. We want the upper tail. So the command to do this is lower tail equal false. Okay. and I get the same result. And of course, so if we look at our density plot that we had here, right? Let me plot this again. Great. So this time, if we want to visualize the area we are computing, x will be, well, the s such that s is strictly higher than 2, sorry. Okay, let me finish this later. Okay, we will have to add some points, but no problem. Remember, this is optional. Y is equal to the density, but only for s greater than 2. Okay, so we are connecting all these points. We are just missing the last point, so that will be 2.1 and 0. Okay, so with the function polygon that I'll copy and paste again from before, now we have the visualization of the area that we are calculating with this command pexp, but with lower tail equal false. So we'll look at the higher tail, okay, of the PDF. And this is it for the pexp and evaluating CDFs. Okay, so this is very important because, like, okay, for the PDF, we know the formula, so we can easily use the calculator to get the PDFs. However, with CDFs, you'd have to calculate an integral, and some, like, especially for the normal distribution, we don't have for the normal distribution, for the chi-square, and for other functions, we don't have a closed form for the CDF of the distribution. You have learned how to use the tables to evaluate these CDFs. Of course, it's much easier, much more precise, much faster to use the R commands. Yes, and in real life it's good to use the table to understand what's happening, but in real life you will really use a software or like RStudio to evaluate these CDFs. Let's move on with the next topic, which is how to evaluate a quantile. Great. So the command to do this is Q for quantile plus the distribution token as usual. So we haven't talked about the normal distribution so far, which is possibly the most common, like the distribution that you'll use most frequently. So this time, in the example, we will consider an x distributed according to a normal distribution. Let's say that it's a standard normal distribution. Okay. So, and we want to evaluate the third quartile. Okay. The command to do so is Q equal Q norm 0.75, because, like, the third quartile corresponds to the quantile 0. The third quartile corresponds to the quantile 0.75. We have to specify, as it suggested, the mean equals 0 and the standard deviation of 1q. So we will explore visually what we are doing. So if S is, we define S as a sequence from -4 to 4 of 0. With increments of 0.1, and D will be the D norm of S. Look, okay, this is quite important. So in this case, I'm supposed to set the mean and the standard deviation of my standard normal. However, if I don't do anything, some standard parameters will be used. So, for example, for the D norm, the standard parameters are mean equals 0 and standard deviation equal 1. So, if I just, like, do this without specifying that the mean is 0 and the standard deviation is 1, then it will be fine, because like the standard parameters for this function are exactly those ones. Okay, so okay, S and D are done. Well, I will, oh no, okay, I have it here, so I'll just like copy and paste the commands. The plot SD type, okay, and this is the PDF of a normal 0, 1. Great, so this is the PDF of a normal. So with the command qnorm, okay, you know already, so I'm computing the quantile. So basically it means that the area before, let's see what this q is. So the quantile is 0.67. It means that the area below this curve up to 0.67, so it would be somewhere here, it's 0.75. Let's display this. Let's have a graphical representation of this. So I will have to define the axis of my polygon. Okay, now I'll skip the explanation, but if you're interested, have a look at this. But however, this is not compulsory. So let me think about it. Okay, then Q, and then Q0. Sorry. Okay, and Y will be equal to CDS. So I'm just like extrapolating those points that are before Q, which is the third quartile, 0, 0. Okay, and we use the usual function polygon. Okay, that's great. So the area under the curve before Q equal 0.6744898, okay, is exactly 0.75. Okay. I'll show you a second example about this, because like this will be very important, very important, this function, even the quantile function for the next week, for the topics in the next weeks. So many times we will have to find the z, okay, such that exactly, so we're thinking about the normal distribution, the standard normal distribution. So find the z such that exactly 5% of the cases are more extreme than z. Okay, more formally, this is find the z such that the probability for x to be lower than minus z plus the probability for x to be higher than z is exactly 0.05. Okay, think about it. So we are finding the z such that the probability that our random variable x, which is normally distributed, is more extreme than z, so either lower than minus z or greater than z, is 0.05. Great. To do this, so to find this z it's equal q norm, so the quantile of a normal distribution with evaluated at, can you think of the, okay, maybe you can pause the video and try to solve this by yourself. So I'll let you like 3 seconds. 1, 2, 3. Okay, did you manage? Okay, not in 3 seconds, but you can pause for as much time as you want, as long as you want. Okay, the answer is 0.975. Okay, and so this is the answer, around 1.96. Why is this? So again, let's do this visually. So we will plot the normal distribution. Okay, I'll just do this to let you visualize what's happening. So bear with me for a second. So I want to plot the distribution before minus z. Okay. Let's minus z 0 should be right. Okay, color red, density 10, and then the same thing but for greater or equal z. Okay, not sure this will work. Okay, it actually worked. Okay, so it kind of works. It's not like perfect, but this is because like we are just like plotting an approximation. If we use a finer discretization here, so okay, so like this, you will have yes, some pretty nice tails. Anyhow, so why were we searching for the 0.975 quantile? So basically, I want to find the z, okay? In this case, it's like 1.96, so the z is here, okay? Such that these tails, so the upper tail and the lower tail of all the points below minus z, all together have an area of 0.05. So in order to do so, this area here, so the upper tail, has to be 0.025, and therefore the lower tail, the lower tail, so from here down, must be 0.975. I hope this is clear, and this will be very useful for the next topics on confidence intervals and hypothesis testing. Last but not least, we will learn how to sample from a distribution. Of course, not from any distribution. This can be like not non-trivial, but from the distributions that we've seen so far, which are all implemented in R. So the common to do this is R for random plus the distribution token. Great. So example. Okay. If X is distributed according to a uniform distribution between 0 and 1, well, okay. So to get one sample, we use the function RUnif, and here you specify the number of samples you want to have, the minimum and the maximum of your uniform distribution. If it's well, the standard uniform is between 0 and 1, okay? As long as you stick to the order, you don't have to specify minimum equal 1 and maximum equal minimum equals 0 and maximum equal 1. But that's up to you. So this is a sample from a uniform distribution. Let's get another one. 0.45, another one. Okay. So if you want to have more than one sample, you can define, you just like, oops, you change 1 to, I don't know, like 100. Great, so you have 100 samples from a distribution. Usually you don't want to just like sample them and see them. You want to store them in a vector, and this is the way to do it. So now we have a new vector with 100 samples from a uniform distribution. Let's look what these look like. So best function to do so is histogram, hist. So I want to plot the sample that I've seen. So you see, we only have 100 samples, and does it look uniform? Well, maybe, I don't know, maybe it doesn't look like amazing. You know that histogram plots the counts here. If you want to have if you want to plot the histogram as a probability, right? So that the area below the histogram is exactly 1, you will have to write a probability true. Okay. So now the area below this histogram is exactly 1. Right, it doesn't look great. Why? Because we only have 100 samples. If we had, okay, let me copy and paste, maybe 1,000, 10,000 samples, it should look much better. Let's see. Yeah, definitely. Okay, we have more bars, but still they look great. Of course, like, it's not perfect. It will take billions of samples to make it perfect, but it's good enough. Okay, let's make another example. So so we sample from a normal distribution, so R norm. We want 1,000 samples, and with mean, the normal distribution, we want it to be a standard normal distribution, so with mean 0 and standard deviation 1. And let's see what the histogram looks like. Okay, it looks good. As you know, you can refine your histogram by specifying, for example, breaks equal 50. So if you want around 50 bars. Okay, it does look good. How can we check that this really resembles a normal distribution? Well, there are many ways. However, the first thing you do is to plot a normal probability PDF on top of it. However, be careful. If we use the function that we've used before, this will like override, this will delete the previous plot. So the function that allows you to plot the PDF of a normal distribution on top of your histogram is the function lines. Nice. Red. Okay. Another parameter that I like to change sometimes is the line width. Okay. So for example, if you put this to, I don't know, 3, you will have a much, I don't know, I think it's just like a nicer line. Okay, so this is how you sample from these distributions. So other distributions. So there are many other distributions that you can easily sample from. These are some that you've seen during this module. So there's the uniform distribution. Okay, so there's the uniform distribution. There's the binomial distribution, the Poisson distribution, exponential, gamma, chi-square, student t distribution, and of course like the normal distribution that we've seen. So recall that these tokens, so unif, binom, poise, are valid for also like the other functions. So if you just have to change this initial part with D if you want to evaluate the PDF, P if you want to evaluate the CDF, Q if you want to evaluate the quantile, and R if you want to draw a sample from one of these distributions. Okay, so the last thing that we look at in this video is a very simple and straightforward simulation example of the weak law of large numbers and the central limit theorem. So let's look at the weak law of large numbers. The weak law of large number tells us that if x1, x2, and so on, so we have a sequence of d random variables, and it doesn't matter how they are distributed, but with a finite mean, then the sample mean converges to the real mean, okay, almost surely, in probability. Okay, but because like the weak law of large numbers, we have this convergence in probability. Let's take 10,000 samples from a Poisson distribution. So we've seen how to do this. So this will be n with lambda. Okay, let's say that we have lambda equal 5 like before. Okay, so R is a a vector with 10,000 samples from a Poisson distribution with parameter lambda. In order to highlight, to visualize this convergence to the mean, we want to define the running average. So this will be the running average, okay, is defined as the cumulative sum of R. So the function cumulative sum, you can look at the help, gives as output the cumulative sum of the input vector. So for example, the cumulative sum of, let's say, of the vector 1, 2, 3 will be 1, 3, 6. So every time the last number is added to the previous ones, okay, 1, 3, 6. So the cumulative sum of R will give us as an output a vector where, like for example, the 10th entry is the sum of all the entries before. And then we divide each entry by its position in this vector. So for example, the 10th entry is divided by 10, and therefore we get the sample mean of the first 10 samples. So you will have to think a bit on these commands. Remember that this is a vector, the cum sum of R is a vector, 1 to n is a vector. This division is applied entry-wise. So basically, like, the running average will be a vector of sample means, which is like increasing with when each sample is added. Okay, how to display this? We plot the running average. Okay, as before, we want to display a line. So this is the running average. So you can see that the sample mean at the beginning is quite fluctuating quite a bit, but in the end, if we look at the sample mean of the first 5,000 samples, well, it has stabilized quite a bit. The real sample mean of a Poisson with parameter lambda is of course lambda, and to display a line at that height, we can use the command abline, okay, to plot an horizontal line with h equal to 5, which is our lambda, and of course maybe to differentiate a bit, color red. Okay, so really this is a display, like really with this plot we can see that the sample mean as n increases approaches the true mean. Of course, this is just an example, but this is true for any kind of distribution, and as long as these random variables are independent and identically distributed. Okay, so the last thing we look at today is the central limit theorem, or let's say a very simple demonstration, very simple showcase of the central limit theorem. So recall that the hypothesis of the central limit theorem is that we have x1, x2, so up to, let's say, xn random variables, which are I, d, so independent, steady distribution. We don't care about the distribution, we care that the expectation of xi, so of O, is mu, so finite, and the variance of xi is sigma square. So they have finite expectation and variance. And the central limit theorem says that the sum of all these xn minus n times the mean divided by the square root of n times the variance, okay, tends to a, like in some sense, tends to a standard normal. Okay, so we will make an experiment to check if this is true for a sequence of standard uniform distribution. So we will have that xi is from a uniform 0, 1. Okay, so first of all, we will set n equal 1, but then of course it will be much higher. And let's define u as a vector with n samples from a uniform distribution. So of course in this case it's just like one sample, but as n increases then we'll have more. Okay, what the theorem says is that if we define z as the sum of all my samples minus n times the mean divided by this number, then this should resemble a standard normal. So u won't be a standard normal, but z, which is defined as the sum of all these people minus n times the mean, okay, what is the mean of a uniform distribution is 0.5 divided by the square root of n times the variance of a uniform distribution, which is 1 over 12. So maybe we can write this here, that in this case the mean is 0.5 and the variance is 1 over 12. Okay, so we'd have that z should be distributed according to a standard normal. So how can we check that this is distributed to a standard normal? Well, we can do this in a, this is an example of Monte Carlo method. So to understand what is the distribution of z, we just sample many times from z and display a histogram that shows the distribution that z should have. So to do this, we use a cycle, okay? Cycles are quite slow in R, but many times are extremely useful. So for I in 10,000, okay, we are telling us our studio that for 1,000 times, our studio should sample n times from a uniform distribution, compute the sum, subtract n times this mean, and divide by this, and put the result in a vector. However, I want to keep recording each of these samples. So the initial z will be empty, okay? With this command, we defined an empty vector, okay? And every time we will concatenate z and add a new z here. Great. So, okay, so let's try this and see what we get. East z. Okay, so this is what the sample mean, the distribution of the sample mean looks like when n is equal 1. So definitely not a normal distribution. In order to compare it to a normal distribution, we can do just what we did before, right? So S from, we define a sequence from -4 to 4, right? With increments of, let's say, 0.01. And then D will be D norm, so the density of a normal distribution evaluated at these points. And of course, we use the command lines. Okay, call equal red. Okay, so we get a line here, but this is just because like we're using the counts instead of the actual probabilities here. So in order to change this, we say that true. We want a probability here, so the area below this histogram should be 1, and now the plot should make more sense. So this clearly does not resemble a normal distribution, but let's look how fast this convergence happens. If we only choose n equal to 2, okay, so each time with this cycle we will sample 2 times from a uniform distribution, compute the sum, take out 2 times the average and then rescale, okay. This looks much better already. So breaks equal 50. Okay. I mean, slightly better, I'd say. Okay, this resembles a more a normal distribution, and you can experiment, but really with 3, with n equal to 3, the similarity between the distribution of the sample mean and a standard normal distribution is really surprising, I think. And of course, as soon as we use n equal to 10, then it will take some seconds. Okay, so of course, as you increase these numbers, your computer might take some time to perform these actions, anyhow. So this is the approximation we have now, really close, like the line is very close to the histogram. I think it's like great. So to sum it up, the central limit theorem tells us that if we consider n IID random variables and we consider this particular transformation, so x1 plus x2 up to xn minus n times the common mean divided by the square root of n times the variance, then this transformation will be normally distributed, okay, according to a standard normal distribution as n tends to infinity. With this particular simulation we have done today, we have also seen something about the speed of convergence. So we've seen that if the random variables are uniformly distributed, then the convergence is pretty fast. With 3 random variables, the distribution of that particular transformation is almost normal, and if we increase n to 10, the similarity with respect to a standard normal distribution is almost perfect. Okay, so this is it for today, for this video. I hope you find it useful, I hope it's clear. I didn't do much editing in the video, so let me know if something is not clear, and I can go over it again and with more details and clarity in the next videos. Thanks for watching, and see you in the next video.